My name is Kelly Jensen. I do all of the alumni relations here at HDSI as well as career services. So I'm happy to bridge the gap today with our alumni spotlight event. We have Camille Dunning here she drove down from the Bay Area to be here in person today, so that's kind of a treat. We do these alumni spotlight events quarterly. They're a really good opportunity for students to learn from alumni who have been through the program, who are out doing industry, maybe working on PhDs, doing all kinds of things in the data science world. So it's a great opportunity to learn, ask questions, network. As I said, we do these quarterly, and we generally alternate between virtual and in-person. So that way, if we've got alumni that are in New York, for example, they still have the opportunity to meet with students. And then those who are a little closer to UCSD, we can bring them in person and pick their brains while they're here. So anyways, I'm going to go ahead and turn it over to Camille. She's got a presentation for you. At the end of the presentation, there will be time for some Q&A, and I'm going to be running around with the microphone for that. So again, thank you guys for coming, and thank you to Camille for being here.
All right, let's get started. Okay. All right. So yeah, thank you guys so much for being here. Great turnout. I love that it looks like some people had to get extra chairs, so that's always a nice sign. Yeah, and I know a lot of you guys have classes to go to and or teach, so I'm very honored you decided to squander your valuable hours with me today. So let's just get right into it. So I'm going to start with a little bit of an interactive activity. I'm going to guess at least one of you here is kind of a GPU nerd, technology nerd, at least one of those. So I'm going to start with just a quick little multiple choice quiz to kind of get in the mood here. And you guys can just feel free to shout out the answers. I don't have any rules. So let's just get into it with this first question. So what is the name of NVIDIA's... Oh, it went off. Okay. What is...
Don't touch the mic.
Don't touch it? Okay. I'm just going to move it down a bit. Okay. Okay. I'm going to stay put. Okay. So what is the name of NVIDIA's latest GPU architecture, delivering 40 times the performance of its predecessor, Hopper? Anyone know? You can just shout it out. Great. If we don't know, I mean, we're here to learn. So the answer to this is going to be Blackwell, which is A. So named after the pioneering statistician, David Blackwell, these GPUs represent our biggest generational leap yet. The Blackwell architecture features 4th generation tensor cores, new transformer engine improvements, and also significantly increased memory bandwidth. Next question will be which NVIDIA hardware platform integrates CPU and GPU technologies to optimize large-scale AI workloads. So either the DGX Spark Station, the Rubin AI Accelerator Platform, the Grace Hopper Superchip, or the Omniverse Compute Node. Anyone might have any idea? Just shout out any random answer.
Grace Hopper.
That's correct. So the GH200 Grace Hopper Superchip is our groundbreaking solution that combines an ARM-based CPU, which is our Grace line of products, with a Hopper GPU on a single package. And this is really cool because it effectively eliminates the bottleneck of moving data between CPU and GPU by creating a unified memory space for data sharing. All right, so what's the name of NVIDIA's family of reasoning-focused LLMs introduced in 2025? Y'all can just shout it out again. All right, so it's going to be the Llama Nemotron. So this is our newest family of reasoning-focused LLMs, which we developed in collaboration with Meta. It's specifically architected to enhance logical reasoning, decision-making, and planning capabilities, which is ideal for agentic AI applications where the systems need to actually execute tasks. So what major breakthrough did NVIDIA achieve with AWS in late 2024 for cloud-based LLM inference? So the DGX cloud expansion, neural interface models or NIMs, the transformer engine optimization, or tensor core scaling. Is it D? Okay, so that's going to be NIMs, neural interface models. It's okay. So NIMs are specialized AI model deployment systems that reduce latency and improve throughput for AI workloads in cloud environments, which I know you guys have worked with in your upper division courses, via sophisticated model optimizations and partitioning techniques. Last question, okay. What platform did NVIDIA unveil at GTC 2025, in case you guys watch Jensen's keynote, as the operating system of an AI factory?
B.
All right, it's going to be D, Dynamo. So yeah, it's an open source software designed to accelerate reasoning model inference at scale. And this really does address another bottleneck in modern AI deployment, is reasoning models require significant computational resources. So this is to just let you guys know that we have an entire stack from hardware all the way up to software. We do a lot more than just making GPUs. So now let's actually do the presentation. So first, who am I? First and foremost, I'm a cat addict. I'm a realism artist. I like to draw. And I'm a hobbyist music producer and sound designer. So while I was at UCSD, I graduated from the HDSI in 2023. I started out my freshman year applying to research scholarships offered by the HDSI. I did some networking around, and I started by doing some data science and NLP internships at San Diego-based startups. I also dabbled around in a research as well through the HDSI undergraduate scholarship, as well as the astronomy lab and the existential robotics lab as well. And then finally, around the summer after my sophomore year, I finally decided to venture into bigger companies. So my first big company internship was with BlackRock in the summer of 2021, where I worked on migrating their post-trade accounting data to Snowflake, terabytes of data. And then in Salesforce the summer after, where I had access to the code bases of all of the applications that were being hosted on Heroku, and doing some cybersecurity scripting to detect phishing. The fall after that, I interned at NVIDIA Omniverse, working on their robotics team and developing synthetic data generation pipelines for robotics environments. And then after that, I had a stint at Tesla, where I did some time series forecasting for Cybertruck manufacturing, as well as additional machine learning work and anomaly detection for torque data and bolt fastening in the actual Tesla factories. So then after the fact, I graduated in 2023. I joined NVIDIA as a deep learning compiler verification engineer working on the Jackson XLA team. And I'm currently residing in San Jose, but hoping to move to a condo in a little bit of a nicer part of the Bay Area, thanks to NVIDIA stock, with my lovely cats on the screen, Bijou and Pom Pom. Okay, so let's talk a bit about the critical role of GPUs in modern AI. I know they, at least when I took at least DSC 102, we at least had like one unit where they touched on AI accelerated hardware. So our company's namesake is NVIDIA, which refers to the Roman goddess of envy, which I have pictured here. So our mission is to create such an advanced set of graphics and AI technology that it genuinely inspires in both admiration and perhaps a little bit of envy among our competitors. So GPUs have absolutely revolutionized AI by enabling massive computation that drastically speeds up the training and, more recently, inference of complex models. Think image recognition, natural language processing, and autonomous driving. And what helps NVIDIA in continuing to push those boundaries of AI is the synergy between high-performance hardware and also our cutting-edge software solutions. So let's just quickly go over NVIDIA's roadmap and how that led the AI shift from CPUs to GPUs. So the 2012 AlexNet breakthrough was a landmark moment, one of the first that showcased the raw power of GPUs for deep learning. So AlexNet drastically outperformed other computer vision models at the time on similar tasks, essentially proving that CPUs weren't just for graphics anymore. The success helped democratize AI research and development across both academia and industry because suddenly smaller labs could train and infer from complex models much faster and more affordably than if they were relying on traditional CPU clusters. A key milestone is the introduction in 2006 of CUDA, which made it easier for developers to program GPUs in familiar languages like C or C++. And this also unlocked like a general purpose computing paradigm for GPUs beyond just graphics. And a big part of this story is how much each new GPU generation, like I mentioned Hopper and Blackwell before, so it typically brings at least a 2 to 3x improvement in AI performance. And this is in large part because each GPU generation increases the number of what's called streaming multiprocessors, or SMs, which handle the actual parallel workloads. And it also boosts memory bandwidth, which is a key factor in feeding data quickly into those SMs. And it also integrates specialized cores, like tensor cores, which accelerate mixed precision arithmetic, like floating point 16, float 32, int 8, which you've probably come across like starting out in your Java course, specifically tuned for deep learning. And finally, the transformer engines were introduced in 2022. Those are optimized specifically for LLMs with transformer-based architectures. So in short, GPUs aren't just faster processors. They embody a parallel first design that dramatically reshapes what's possible in AI. And as AI models grow more complex, we expect to see further specialized hardware improvements from memory hierarchy tweaks, going back to DSC 102, and next-gen tensor processing units. So let's go a bit into why exactly GPUs revolutionized AI, their architectural advantages. So modern GPUs have thousands of cores compared to what we see in CPUs, which usually amounts to just a few dozen. And this means that massive parallelism means that GPUs can execute many operations concurrently. But it's not just about having more cores, but having specialized cores that are designed for high throughput and tightly packed operations. And beyond raw core count, GPUs also come with advanced memory architectures like stacked memory and specialized caches to feed their parallel compute engines. So we have a nice synergy of memory bandwidth and parallel cores, and that's tailor-made for the dense iterative operations that define neural networks. And historically, training complex models on CPU clusters could run into the millions of dollars in hardware, power, and cooling. But GPUs slash those costs by orders of magnitude, sometimes to the thousands or even the hundreds of dollars, particularly when we leverage cloud services like AWS that let you pay for only what you need. And it's a budget-friendly approach. That means that smaller labs and startups can now compete with big tech companies, and it's effectively leveling the playing field. And the important part is when training becomes cheaper, that means you can do it more frequently and iterate on your models faster. And this creates a shorter feedback loop that drives faster breakthroughs. So over the past few years, we've seen model sizes absolutely skyrocket. So BERT from Google had around 340 million parameters. GPT-3 jumped to 175 billion. And now some of the modern LLMs are rumored to be beyond the trillion parameter mark and even into the multiple trillions. And these leaps in scale require not just a single powerful GPU, but clusters of GPU working together, usually in at least one rack or many. But of course, a huge challenge here is coordinating multiple GPUs without bogging them down in intense communication overhead. This is where innovations like NVLink, InfiniBand, and high bandwidth interconnects come in. And when you're splitting massive models across multiple devices, these technologies let GPUs exchange data extremely quickly. And to fully harness the multi-GPU systems, AI frameworks and compilers now optimize code for distributed training. They automatically handle data parallel, tensor parallel, and model parallel strategies like partitioning model layers, for example, or data batches across different GPUs. And we have our own software stacks, including libraries like Nickel, to make it easier for developers to achieve near linear scaling when adding more GPUs when running their AI workloads. And with these trillion parameter models, even minimal inefficiencies can balloon costs and training times. That's why advanced optimizations like reduce precision data types, optimize all reduced algorithms, and smart partitioning are absolutely vital. And these improvements can shave weeks off training time and slash infrastructure costs. These multi-GPU setups, they may seem very expensive up front, but if we tackle extremely large models in parallel, we'll dramatically cut the total time and energy needed to train, meaning, again, more experiments and less time. So exactly like how is this gonna affect you guys? So as the AI landscape evolves at a breakneck pace, there's a rapidly growing need for data scientists who understand how to leverage parallel computing, distributive training, and specialized libraries. In other words, it's really no longer just about knowing machine learning algorithms like DSC 140A, great course. It's also about understanding the platforms that make these algorithms run efficiently at scale. I'm going to go into how being fluent in GPU-accelerated data science gives you a competitive advantage as AI continues to expand into every corner of industry and academia. So first we have many potential changing skill requirements. So today's data scientists increasingly need to know how their frameworks tap into GPU resources. This doesn't need to always be about writing like low-level GPU kernels from scratch in maybe C or C++, but it does involve understanding how tensor operations map onto GPU threads or blocks or warps. This might include recognizing when data loading bottlenecks your GPU or how asynchronous CPU and operations can overlap to reduce idle time. And so it's nice overall to have just a mental model of the GPU's concurrency model and memory hierarchy to boost that training efficiency. And another really important point here, which I run into at my work at NVIDIA very frequently, these GPUs are super powerful, but they're not always abundant and they're super expensive. Cloud environments, as you guys have probably experienced, they often charge by the minute or hour for GPU usage. And on-prem clusters, even the ones we have at NVIDIA, they're always shared resources, like whether I want to go into a cluster of B200s, H100s, or A100s, if I want to submit a Slurm job to get access to a GPU node on those clusters, I only get it about half of the time because these GPUs simply aren't abundant enough and they're in such high demand. But to circumvent this, we're seeing techniques like model and gradient checkpointing, mixed precision, and layer-wise parallelism. These are no longer just nice-to-have features. They can be the difference between training a model in days versus weeks, and paying thousands of dollars versus paying tens of thousands of dollars. And additionally, choosing the right GPU instance type or optimizing batch sizes can have huge cost implementations. The more you understand the memory footprint of your models and parallel workloads, the more effective you'll be in budgeting and scaling your AI experiments. And single GPU training is simply just becoming increasingly unrealistic as models balloon into the billions and trillions of parameters. You'll need to design systems that coordinate multiple GPUs, often across multiple different servers, while managing communications overhead as well. And practical distributed strategies, as they've gone over in DSC 102, might include data parallelism, splitting your data set across multiple GPUs, or model parallelism, dividing the model's layers or parameters. And tools like DeepSpeed or PyTorch's native distributed APIs, they already automate some of this setup, but designing a truly efficient system requires an understanding of maybe cluster topologies, network bandwidth, and memory sharing, data access patterns. And beyond raw training, you'll also need to consider fault tolerance and reproducibility. So a background in distributed systems concepts, even at a high level, is really becoming increasingly valuable. So overall, I think this means that the data scientist of tomorrow is part statistician, part software engineer, but also part systems architect. But I think this is also going to create a lot of new learning opportunities for you, and I've come across this in my coursework at the HDSI as well. So in the past, only large companies or well-funded labs had the resources to maintain powerful on-premise GPU clusters. And today, cloud providers like AWS, they offer scalable GPU instances on demand, meaning students can rent the exact horsepower they need for a project, and they only pay for what they use, which lowers barriers to entry significantly. You can experiment with bigger models without needing upfront capital or dedicated hardware. And this is also leading to the development of many specialized courses, like universities and online platforms are increasingly offering classes on GPU programming, distributed machine learning, and HPC fundamentals. These courses go beyond the standard data science topics, covering everything from concurrency models to memory optimizations. And it's exciting that with the combination of accessible GPU resources and better educational materials, students can now tackle research problems once reserved for big tech and advanced R&D groups. It's absolutely feasible now for a student or a student research team to achieve groundbreaking results on a relatively modest AI budget. And of course, this might influence career paths as well, creating new emerging roles. The ML infrastructure engineer might focus on building and maintaining the backend systems that support large-scale AI. This includes maybe configuring the GPU clusters, managing distributed training frameworks, and facilitating smooth model deployment, which aligns pretty closely with what I personally do at NVIDIA every day. The AI systems designer might specialize in selecting and orchestrating hardware interconnects like NVLink or InfiniBand, and parallelization strategies for optimal performance. The compiler optimization engineer might work on tuning deep learning compilers and libraries so that neural network operations map efficiently to GPUs. This is the org I actually work under at NVIDIA. And I'm actually hoping to give some guest lectures at some courses on deep learning compilers, if you guys are interested. So for many of these roles, you're going to find that some of these people, and myself definitely included, they'll have a T-shaped skills profile. So for example, like a broad exposure for systems and infrastructure, but plus deep expertise in a specific ML domain, which this is going to position you to both innovate, but also do well in a collaborative environment and troubleshoot at any level of the stack. And as AI models continue to evolve, the underlying hardware will keep changing too. So individuals who know how to adapt to new GPU architectures and specialized hardware, whether that's through mixed precision computing, on-the-fly compiler optimizations, or advanced distribution techniques, you are going to remain highly employable, and you can pivot quickly as new technologies emerge. So when we talk about T-shaped skills, we're referring to a combination, as previously mentioned, of broad knowledge plus one area of deep expertise. So the horizontal bar of like the T you can think of, it represents essential breadth, which I think HDSI does a great job of teaching. Areas like technical literacy, systems thinking, business context, ethical considerations, and communication. The vertical bar of the T, which I've really focused on developing most while I was at NVIDIA after I graduated, this represents the area that you choose to specialize in. So this could be an infrastructure specialty. Maybe you're the go-to person for scaling machine learning on large GPU clusters. Or you might aim to become a domain expert in healthcare, finance, climate science, applying AI solutions in these fields. Alternatively, you could focus on algorithmic innovation, like how models are structured or trained. But ultimately, the key question is, where do you want to develop your deep expertise after you graduate? So identifying that vertical focus is what's going to give you a strong competitive edge, while your horizontal cross-functional skills, they're going to still make you very valuable in any collaborative environment. So it's this blend of depth and breadth that helps you stay adaptable. And to connect this a bit to my experience, I studied so many different things while I was at UCSD, later on LLMs and agents. While I was at Tesla, I capitalized on time series forecasting. I also, when I was in DS3 while I was at UCSD, I also did a time series forecasting project, Python and efficient SQL through courses like DSC 80, DSC 100, application design patterns, open source software, which is what I'm also working on at NVIDIA right now, graph neural networks, which I actually did my capstone project on this, and ML and deep learning frameworks like CAF, Theano, PyTorch, and TensorFlow, which is being increasingly replaced by JAX now. But my depth right now is focusing on deep learning compilers. So I'm thinking about how to close the gap between theoretical and achieved flops, working on the layer between the machine learning framework code and the GPU kernel code. You still need to actually compile that code and figure out how to represent that neural network as a computational graph. So also optimizing memory access patterns, fusing fusion operations, so possibly any fusing nodes together in that computational graph. So maybe fusing a matrix multiplication operation with an addition operation for a scalar addition for more sped up execution. And also the balance between computation and communication is, again, very often we're working on compiling these models in a distributed environment. So after this, as someone who works in NVIDIA, I see firsthand how AI is reshaping countless industries, and education is no exception. And AI has become so ubiquitous in education now that students that you guys, I'm assuming you now use it for everything from brainstorming research ideas to generating code snippets for your problem sets. But I can imagine that with that ubiquity, it comes a lot of uncertainty, maybe even despair, about what skills to focus on, how to harness AI's capabilities responsibly, and where it fits into building you a solid educational foundation still. So to help you navigate this, I actually want to share a few different schools of thought backed by insights from real AI experts and academics who've studied AI's impact on learning. And I think it's going to be interesting to just approach this from different perspectives, like a more optimistic perspective, a more critical perspective, as well as a more pragmatic one. But it's important to note that simply having access to advanced hardware in AI models doesn't automatically guarantee you deeper learning. There is still a human element, your curiosity, your ability to interpret and validate results that AI can never replace. So that's why an understanding of ethical considerations, data biases, and the broader societal implications of AI is also crucial. And I think academic programs are doing a great job of increasingly weaving these topics into their curricula as well. So the first school of thought that I've kind of coined from this, so the transformational optimist stance is about harnessing AI as a force multiplier. So LLMs can be viewed as a democratizing force in education by making advanced computational capabilities accessible to more learners regardless of their location or their budget. So Ethan and Lilac Malik at the Wharton School, they encapsulate this concept in the they encapsulate the concept of these technologies serving as capability amplifiers in this paper, assigning AI 7 approaches for students in 2023. So they outline roles such as an AI tutor, an AI mentor, an AI teammate, an AI student, and an AI tool. I believe there was, of course, 7 in total. So for instance, the authors tested an AI tutor concept in advanced coursework like finance and data analytics, where iterative feedback from an LLM helped students tackle problem sets. And of course, as we probably expect, students who actively talked back to the model, probing its reasoning, asking follow-up questions, challenging its assumptions, they demonstrated a deeper mastery of the material than those who simply consumed the AI-generated answers. They also proposed the idea of an AI coach for focusing on developing higher-level skills, such as strategic thinking and metacognition. Unlike a simple chatbot, a well-implemented AI coach would actually push you to justify or refine your ideas. And perhaps the most sophisticated approach is the AI student model, where learners actually teach the AI a concept. So making the AI learn from you forces you to articulate your reasoning, test your explanations, and address potential knowledge gaps. And what's particularly noteworthy here is their emphasis on domain-specific customization. In pilot programs, LLMs fine-tuned on specific course material provided more targeted and accurate feedback. And of course, this opens another can of worms, like ensuring consistent AI quality control and mitigating biases introduced by specialized training data. But that's what we're here to learn about, what we're here to learn how to fix. But ultimately, the school of thought redefines the learning contract between professors and students. And students have the potential to use AI as both a tool and a partner, requiring high-level skills in prompt engineering, ethical stewardship, critical analysis, while educators gain more time for personalized mentorship. Now I'm going to move on to the critical skeptics, which these will raise concerns about relying too heavily on LLMs in education. One major worry cited is skill atrophy, simply from students becoming over-reliant on AI-generated answers. There's also skepticism about accuracy and biases of AI outputs, as well as the extent to which LLMs truly understand the material. So Darren Acemoglu, an MIT economist and co-author of Power and Progress, Our 1,000-Year Struggle Over Technology and Prosperity, he questions the assumption of whether AI will just automatically boost productivity. To him, he thinks that's a very blanket assumption to make. So he actually places AI in the context of historical technology disruptions, and he argued that skill-based technologies can exacerbate maybe income and opportunity gaps instead of closing those gaps unless carefully managed. So he points to the digital divide as a danger whereby wealthier institutions and students benefit from AI tools, where under-resourced populations might fall further behind. So rather than viewing AI integration as inevitable or uniformly positive, so kind of taking a technological determinist approach, critical skeptics emphasize that we must ask, is the technology merely replacing human expertise or complementing it? And Acemoglu believes that complementary technologies can genuinely enhance human work, but an automation-centric approach, or just excessive automation in general, we risk devaluing human roles and may lead to job displacement. But basically, we can't embrace automation for its own sake. We need something called machine usefulness, where AI supplements human expertise rather than displacing it. So from this standpoint, the issue isn't just whether AI works. It's whether it serves broader social and educational goals, such as equitable skill development and meaningful employment. And finally, I've coined the pragmatic integrationists. They see large language models not as replacements for educators or learners, but as tools that augment human intelligence. So I thought this was an interesting paper. So Eric Brynjolfsson from Stanford's Digital Economy Lab, he emphasizes in this work, particularly in the Turing trap and also generative AI work, that this focuses on actually changing the benchmarks we use for these models. That we should shift from the traditional benchmark of AI matching human capabilities, but rather designing systems where humans and AI collaborate. So in the beginning, this is where we should be evaluating in the beginning of the research process. This is what we should be evaluating. So he points out that focusing solely on AI's ability to replicate or replace human tasks overlooks the potential that it can be a trap, since it overlooks the potential for complementary and collaborative skills. So translating this into an educational context, we can imagine students getting a head start in mastering challenging material with an AI co-pilot. But just as important as that is rethinking course design as assessments so that AI strengths, pattern recognition, and rapid information retrieval, they amplify our creativity rather than supplanting it. And this might mean structuring learning tasks to require uniquely human approaches, even in highly technical fields, like judgment, ethics, original thinking, rather than including any tasks at all that AI can simply do on its own. So adopting AI effectively requires redesigning workflows and benchmarks according to this view. And again, rather than testing whether AI can fool a human, which is what the Turing test focuses on, he suggests that we evaluate instead how well AI and humans can work together to achieve new levels of performance or insight. So again, this could mean new forms of assessment that let students actually showcase how they collaborate with the AI. So ultimately, this pragmatic integrationist approach encourages us to move beyond the mindset of AI is doing simply what humans can do. And instead, we can leverage these advantages of LLMs like scalability, instant feedback, and vast content retention to create different educational experiences. So from this, these are kind of some thoughts that I gathered from all of these schools of thought. They approach this issue all from different angles, but I think they kind of lead to the same goal at the end. So the saying that the struggle is where the learning happens is especially something that I believe is relevant in the AI age. Sometimes, I'm sure as you've seen in your experience in your studies, AI tools can short-circuit that struggle by handing us answers too quickly. And when we let an LLM solve a problem without stepping through our own reasoning, we risk missing out on identifying and correcting our own misconceptions. Hence, this would be the crux of what it's basically a metacognitive paradox. Is AI helping me discover and resolve my knowledge gaps, or is it simply just bypassing them? And so historically, education has focused on memorizing facts or formulas, but of course, content retention is now much less critical since AI can retrieve and generate information almost instantaneously. And what grows more valuable is the ability to judge and interpret information. In other words, knowing how to question and contextualize data is more important than possessing that data in your memory and actually having that knowledge itself. So, for example, if an AI suggests a scientific paper, can you gauge its credibility? If an AI writes code, can you debug and verify it? When you develop these skills, you'll see that learning is effectively transformed from just collecting knowledge to evaluating and synthesizing knowledge. And it might be to the point where collecting knowledge is completely obsolete. And of course, there's the risk of the competency trap, so that when AI makes everything so certainly easy, we can just become complacent. So today's AI efficiency might cause us to cling onto old methods or resist new technologies that could actually be better in the long term. And this is similar to how organizations might stick with legacy tools or methods because they're simply good enough. Because even though there are more advanced alternatives that could potentially yield greater benefits. So the key here is to stay proactive. So keep refining your skills, exploring new approaches, and remembering that AI is still evolving itself and it's never a fixed endpoint. And when you continue to embrace AI in your studies, you need to balance convenience with deeper engagement. And there's this continuing mindset shift from, I want to emphasize, from mere retention to critical evaluation. So if anything, it encourages you to push yourself further out of any sort of comfort zone. And finally, another uncertainty you might run into is attribution, like taking ownership of what you're learning. So, like, how much credit can I take if AI does most of the heavy lifting in this assignment? And if a system proposes an entire solution, did you actually learn? We need frameworks, I believe, that actually clarify how much of a solution comes from you versus the AI. So this can mean, like in some advanced settings, you may be required to annotate or explain which portions are AI generated and how they verified these steps. That way you can still demonstrate mastery rather than outsourcing all of your cognition to an algorithm. So we also treat AI like an expert model. We're not just grabbing the end result. We're delving into how the AI got there. This could involve, again, reverse engineering the AI outputs, asking it for alternative approaches or detailed reasoning, then comparing those to your own. And for instance, if AI produces code or a proof, request multiple versions of that proof or expansions at each step as well, and piece together and understand each of those underlying principles. So you want to use that AI response as a springboard into deeper inquiry. So it's even a lot more of a responsibility. And finally, a key meta skill is recognizing when the AI is reliable or not. So just as experts learn to gauge the trustworthiness of different sources, we need to assess when an AI might be hallucinating, overlooking edge cases or injecting biases, which I still constantly run into using models like Claude at work every day. So developing AI intuition here might mean noticing warning signs, contradictory statements, leaps in logic, or an inability to cite credible references. And this meta skill is what's going to make you more adaptable and resilient when AI inevitably fails. Because you're going to know how to pivot, how to cross-check, and how to retain ownership of what you're actually learning, which was definitely some uncertainty I ran into as I was at the tail end of my education here. So finally, as we wrap up, I want to emphasize that your uniquely human capacities, meaning-making, ethical judgment, and creative connection, they're never going to be eclipsed by AI. And as someone who works at NVIDIA, I felt a responsibility to reassure you guys of this. So, in fact, they become more valuable as technology takes over routine tasks. Your ability to interpret subtle context, imagining possibilities beyond the data, and exercising moral discernment, they can never be automated. When I talk about your humanity as a superpower, I'm pointing to everything that makes you adaptable, empathetic, capable of seeing the bigger picture. So AI might supply information, but it's your perspective that weaves it into a deeper narrative, your sense of right and wrong that applies it ethically, and your creativity that sparks something entirely new. So that's going to be it for this presentation.
Wow, impressive, no? Really got all that? That's a lot of information. Thank you, Camille. You guys ready with some questions? Don't be shy. We've only got 15 minutes, so hands up.
Yes.
Could you tell me about your role at NVIDIA? You mentioned something about JAX. What is that?
Yes. So if you've seen TensorFlow before, JAX is from Google, and it's essentially what is replacing TensorFlow. It's Google's equivalent of PyTorch. And I don't always work directly on JAX, but I actually focus a bit more on the XLA compiler, which is the layer under JAX, which actually, like I mentioned, it maps all of the operations to the GPU components, like the threads and the warps and the blocks. So not only have I contributed my insights to that open source software, I also work on building the infrastructure from the ground up to run these test beds on like a nightly cadence and expand that support to our Hopper architecture, our Ampere architecture, and our Blackwell architecture with different versions of CUDA, like cuDNN, our entire software stack too. So test bed development is also a big component of my work as well. And I'm also working on benchmarking JAX against all of those different configurations within the NVIDIA stack. So I'll build the infrastructure for correctness testing, so like whether it passes all the unit tests, but also is within a threshold of accuracy or mean squared error loss, or whichever metric the model you're testing might use. So.
Other questions?
You mentioned something about having T expertise and specializing in one thing. Do you have any advice for our students on how we can figure out what we want to specialize in, how can we get that experience and realize this is what I want to do for the rest of my life kind of deal?
Yeah, so my experience, it definitely, like at least the vertical bar there, that it definitely switched a lot of times, and there's nothing wrong with that. And what I think college really specializes in, it gives you the breadth and it gives you all of those tools. Because I think like it's going to be very rare for someone just to specialize purely in SQL or purely in Python, like any specific programming languages. You still want to be good at those, but that's not going to give you enough of a competitive edge. So when you're thinking of like what you want to develop your expertise in, think of what's going to give you that competitive edge. Because these breadth skills, that's just going to be what makes you good in a collaborative environment, and that's going to tell you, and that's going to gauge how well you work with others. But so for me, my specialization, it shifted a lot of times. I think when I was at UCSD, I wanted to specialize in robotics. That was when I was doing research here and that, but also when I interned at NVIDIA Omniverse as well. But then that changed later on when I got my actual current full-time role at NVIDIA, which I'm actually interested in developing a very deep expertise in more of the hardware side of things. And I'm actually very interested in bringing accelerated hardware curriculum to the data science department here at UCSD, and not just the hardware where you might write the GPU kernels, the layers between like a software, like our framework code, and the GPU kernels as well. And that's where the deep learning compilers come in. And I would be really excited to actually form some kind of industry partnership with NVIDIA via the HDSI, so we can teach all of those layers of the stack, because I think it's becoming increasingly important for you future data scientists to know. Yes?
So how did you approach your capstone project? What made you choose the topic that you did? When did you start planning for it? And kind of how does that relate to the role you're in right now?
Yeah, I got to be honest, I had some really smart people on my team for my capstone project. And I was really excited about it because naturally I'm just a very, very project-driven person. I wasn't always the best at like taking tests and just retaining knowledge. I was a lot more enthusiastic about writing papers, crafting a presentation. But yeah, when you're choosing your capstone, they're already going to have like the domains laid out for you. I don't know if you're just about to enroll in it like next quarter or whether you're already enrolled, but so they're going to have all of those options laid out for you. And in your first quarter, they're going to teach you everything within that domain. And then you might go through that first quarter finding holes in what they're teaching you, finding potential gaps. And then you're going to spend your second quarter kind of trying to address those gaps from your own angle, if that makes sense. So it was a very interesting experience. Yeah. Yes.
You mentioned about your research experience about astrophysics and applying that to data science. Could you just speak more about how that research experience helped you land your role in the industry?
Yeah. So I think. It was actually when I was doing the research with the Cool Star Lab at UCSD, when we had to run experiments classifying, like based off of like spectra data from stars, classifying whether that sun might be coming from a binary star system or just a single standalone sun. I had to run so many experiments. And these weren't always reproducible. How am I going to share these experiments with my team members? How am I going to store these results? How am I going to track which hyperparameters I used? And how am I going to just run these experiments repeatedly? So I figured out that I really had to automate this, and I had to build my own framework, and I had to develop sort of an environment to run these experiments on my own. So that was kind of a canon event for me, where I realized I like ML ops, I like ML infrastructure. I want to help people. Run their AI workloads as efficiently as possible, and also make their results as fault tolerant and reproducible as possible. So I think that was when I really started doubling down and teaching myself software engineering, best practices, and getting feedback from other engineers how they can reproduce and get the same results that I was able to attain. And I think NVIDIA is pretty much the best place for that. Like what we do here is, at least what I do as a verification engineer on my team, I just want to make life as easy for other engineers as possible. So I think, yes, definitely that astronomy research lab, which I didn't really expect it to be, but it was definitely kind of a canon event for me. It was when I realized I wanted to work in ML infrastructure.
I have a question for the audience. How many in this room are currently searching for an internship?
Yeah.
Right? A few.
Been there.
So she's got some really great internship experience at a lot of different big companies. I would like to know, how did you get your foot in the door? What helped get you started? What were some challenges and successes along the way to get you where you are today?
So I got to be honest. When I was a freshman, I spent an unhealthy amount of time on LinkedIn. So, but not only that, like I was also in DS3. Like I started in the project subcommittee. There were some very, very smart people on my team. So I would just stalk them on LinkedIn all night, and I would see what programs they did because they're like BlackRock, which was my first big company internship. They did offer internships specifically for sophomores. So I just kind of sifted through all these LinkedIn profiles, like what did they do their freshman year and their sophomore year, because that's probably going to imply to me that these programs are a bit easier to get into. They do have reserved positions for lower classmen. So really just sifting through LinkedIn profiles, that was able to help me narrow down the lists of places I wanted to apply at.
Great, thank you.
Hi, thank you so much, Camille, for the great talk. So for NVIDIA, I have two questions. First question is, I know most companies, they have like LLMs or AI integrated into employee workflow, so I wonder if NVIDIA do the same.
Yes. So you've heard of Cursor? Yeah. So they're actually like forcing all of us employees to kind of make that our native IDE by the end of the year. In a previous section of my presentation, towards the very end, actually, I talked about a competency trap, us getting complacement. So I'm actually very guilty of that because I'm so used to just copying and pasting my code into like Claude online because I feel like it's just good enough already, and maybe I don't want to learn how to use Cursor because it's a little bit of a learning curve apparently. Like in my company, there are some teams, like IT teams, that'll hold office hours on how to adopt Cursor into your workflow, and I've been very recalcitrant in doing that myself. So I've also been kind of trapped within that competency trap. But yes, we're pushing very hard to use those LLMs, those Copilot assistants into our native coding experience. But we also, of course, have LLMs that are fine-tuned through our like internal code index and our internal company index too. We have something called NV search, I believe, and you'll see Google will have the same thing that's built on their Gemini model. So companies have a lot of their own internal versions of like ChatGPT, which is simply just which are simply fine-tuned on their code bases.
Cool. Second question is, DeepSeek happened, and people's needs for, they significantly reduce the need for hardware because their LLMs is like, consumes less power, and NVIDIA's stock, I think, all the stock kind of go down for big tech. I was wondering, like, when that happened, what was your experience about?
Yeah. I think with the stock drops, at least for now, I think these are usually very short-term kind of shocks that'll hit our company. But I think also it was that DeepSeek was the moment NVIDIA realized we need to pivot to inference. There's a great opportunity and not a big hole in the market, but a great opportunity for our hardware to target inference as well, because DeepSeek did very well at that. So, if anything, these stock drops, they're completely normal. They're not going to indicate like a company going under any sort of recession. It just might tell us when we need to pivot, if that makes sense. So. Our next line of GPUs is actually going to focus a lot more on inference, and as is our new software stack with distributed systems.
Thank you so much.
Sure. All right, we have a question in the front. We're back. Yeah.
Hey, hi. Thanks for the talk. I would like to ask, you talked about horizontals and the verticals. So what are the verticals which NVIDIA is interested in hiring from?
Yeah, it's because NVIDIA, I'd say it's even harder to answer for NVIDIA than like a purely application software company like Google or Facebook, because we work on hardware, we work on compilers, We work on like Linux, like x86, LLVM compilers, like, and we work on robotics environments. So we work in healthcare. We do absolutely everything, not just GPUs. So it's NVIDIA, in my experience, was the single most team-specific company to interview for. So I'd say all I would have to say on that is it highly depends on your team. But I'd say in general, there was one stint I did at UCSD where I worked in a distributed environment interning for the San Diego Supercomputer Center. So simply, I would say distributed training, distributed systems. That's very important because single GPU training, again, like I mentioned, is simply just unrealistic now. And memory access patterns, memory hierarchy. So basically anything they teach you in DSC 102, I remember that course really stuck out to me like so much as being like one of the most instrumental as in what I learned at UCSD. So they're really going to like it if you know machine learning, if you know data science and statistics concepts, but you're probably, when you get to NVIDIA, you're likely going to be contributing to those frameworks. So they want to know how you're going to improve these frameworks, like PyTorch, for example, to run their AI workloads most efficiently on an NVIDIA GPU. So it's kind of a lot. It's really highly team specific, but pay attention in DSC 102. Yeah.
All right, final question. We have one up here.
Yeah, you mentioned distributed systems numerous times and how important it is to get a mastery of that. I was wondering, how would you show that you do have an understanding of distributed systems to employers?
Mm-hmm. So I'd say projects definitely won't hurt. In AWS, I believe you can get access to a cluster, and I would say, but getting research opportunities with different labs, like in one robotics lab, I had access to the Nautilus cluster, and in the San Diego Supercomputer Center, I think it was called Voyager. The name kind of eludes me now, but I did single GPU setups, like writing Jupyter notebooks, kind of demonstrating how to run an AI workload on a single GPU setup, but also as a multi-GPU setup. And I think getting research roles, you're going to be more likely to get access to those on-premise clusters. So, and I know UCSD is probably exponentially improving in that as well. So I think research roles at this point are going to is going to be the most straightforward way for you to have access to this hardware.
All right, how about a round of applause?
Thank you so much.
That is amazing. Thank you so much for all the information, all your expertise, and taking the time to be here today.
Of course, thank you.
Do you have a couple minutes if people want to hang out and talk for a little bit? I don't want
Yeah, I don't bite.
to stay if you've got to go.
Yeah, no problem.
Okay.